When we think about the internet, we usually picture a cloud. We look at the smooth glass of a smartphone and imagine a frictionless, weightless portal to a purely digital world. But the computers from 40 years ago tell a different story. These machines were heavy, beige boxes of metal and plastic that made their physical requirements impossible to ignore. Modern devices have shrunk, but they haven't escaped the physical world. Every glowing screen and lightning-fast processor still requires moving millions of tons of dirt, rock, and elements from the Earth's crust. When you buy a new piece of consumer technology, you are actually purchasing a tiny, highly engineered slice of the volatile global commodity market. Understanding why technology costs what it does requires looking past the software and examining the raw materials it is built from. Take apart a standard computer, and the code disappears. You are left with global resources. Half of its weight comes from extracted metals. To connect microchips and power circuit boards, a device requires substantial copper wiring to transport electricity. Extracting that copper from the earth involves massive industrial consumption. A single copper mine can use up to 500 gallons of water every second. That is just one element. To build modern components, manufacturers globally source a precise recipe of lithium, tin, silver, gold, nickel, and aluminum. Every microsecond of computing power your laptop generates is physically chained to the massive scale of industrial global mining. Beyond the extracted metals, there is a hidden layer of structural materials and physical labor required to actually assemble these devices. Manufacturers mold thousands of tons of plastics into protective casings and rely on specialized ceramics to act as insulators. An insulator is a material that resists the flow of electricity, which is critical for protecting delicate internal parts from shorting out. Bringing all these pieces together requires a constant flow of industrial chemicals. The production lines consume vast amounts of solvents and vases to strip away microscopic impurities and degrease components before final assembly. Because these chemical supplies must be purchased on an ongoing basis, electronics manufacturers gain a strategic advantage by locating their operations directly next to key chemical producers. The entire assembly process relies on a continuous, energy-heavy chemical synthesis to ensure every component meets precision standards. Because electronics require such a specific blend of raw materials, the global commodity market creates an ongoing point of financial insecurity for the entire sector. Any sudden shift in the global supply or demand for these precise elements rapidly alters how much they cost to procure. This chart tracks how a hypothetical supply chain reacts to market changes. When the futures price for a raw material spikes, it creates an immediate variable cost increase that disrupts a manufacturer's entire pipeline. As that extracted material moves along the chain, the total expense compounds. The energy required just to transport these heavy raw ores and finished components adds even more cost into the system. By the time the flowchart reaches the end of the line, that initial spike in the commodity market has forced the final price tag of the consumer product to rise on the store shelf. Even the most advanced tech companies in the world remain vulnerable to the unpredictable swings of the raw dirt and metal markets. How do electronics companies defend themselves against crippling material costs and supply chain insecurity? Their primary defense mechanism is heavy funding in research and development. Tech companies pour resources into the materials and chemical sectors to invent advanced compounds. They are constantly searching for substitute materials. If a primary metal or chemical becomes cost-prohibitive to source, engineers proactively identify and swap in these alternative ingredients to keep production lines running. This forced adaptation drives technological advancement. Synthesizing new materials leads to better hardware designs and improves the overall longevity of the devices we use every day. By improving the longevity of individual components through these synthetic breakthroughs, manufacturers can slow the rate of extraction and reduce the total environmental footprint of their hardware over time. With millions of new customers in emerging market economies demanding affordable technology, this intensive materials research is set to accelerate. Ultimately, technological dominance relies on the ability to efficiently synthesize the physical elements of the Earth.